Hi, I'm Rick Sellens, and in this video I'd like to talk a little bit about the equipment and the measurements you're going to make in this first lift and drag lab that you're doing in MEC 399. The objectives in this lab are to improve your understanding of flat plate boundary layers and the flow over airfoils, gain some experience using a wind tunnel, and also experience doing some detailed flow measurements, not just some overall measurements, but some detailed velocity measurements. And finally, to get some more experience reducing and analyzing this flow data to pull more information out of it. You're going to use a wind tunnel. That's the first thing. And a wind tunnel, the whole objective with a wind tunnel is to provide a controlled flow that approximates the uniform flow that you'd see in an open flow in the atmosphere, an unbounded flow field. This wind tunnel is Flowtech 1440. It's an open return type. What that means is the air goes in here, goes through the test section, comes out the other end through the fan, and then circulates through the room and back in again. That's in contrast to a closed return where there'd be a pipe connecting the outlet back to the inlet. It's got an axial fan that's located here in the photo or here in this schematic, and it pulls the air through. The incoming air goes in through this set of honeycomb flow straighteners, which reduce the turbulence and make sure the flow is all going in a straight line. And then it's squeezed in this contraction section to get the flow to accelerate and also to dissipate some turbulence. So that by the time it gets into the test section, in the middle here, it's going quite fast. It has very low turbulence. We can get up to 33.5 meters per second airspeed with a turbulence level of less than 1/5 of 1%. So that's really good. And you can measure how fast the flow is going through the test section by a hot wire film probe that we've placed in the test section. So you can use the controls over here to set the speed of the airflow in the wind tunnel. Now, this wind tunnel is just big enough and fast enough to start seeing transition in a boundary layer within the wind tunnel. This is pretty much the limit on the size of wind tunnels that would be useful for understanding things in a course in fluid mechanics. So if we wanted to see a fully turbulent boundary layer, we can use roughness elements to cause transition much sooner. So where a simple boundary layer on a flat plate would first be laminar, there'd be a period where it was going through transition, and then finally it would become fully turbulent out here after quite some distance downstream. In our experiments, we can put some roughness at the leading edge of the plate and use that to generate disruption and instability in the flow so that we'll have turbulence much sooner. Now, the turbulence level that you get depends on the Reynolds number, and the Reynolds number for a boundary layer is defined using a characteristic length as the distance along the boundary layer. So what you'll see is in the airfoil measurements that we're going to do, we're looking at a Reynolds number down here somewhere between 10 to the 5th and 10 to the 6th, meaning that we're still in a laminar flow regime. However, when we get onto the flat plate and we have roughness elements, we'll have experienced transition and we'll get up into the higher Reynolds numbers and also into a fully rough turbulent boundary layer. Once we've got these flows going on in the wind tunnel, you're going to need to make some measurements. And our objectives here are to make all of our measurements with pressure transducers, and we're going to use pitot tubes to help us get the velocity in terms of measurable pressures. We have single pitot tubes like this that we'll use when we're working with the flat plate, and we have multiple pitot tubes in a rake like this that we'll use when we're measuring in the wake behind the airfoil. Each individual pitot tube looks something like this, and what you get is the stagnation pressure when the flow comes and hits the end of this pitot tube. that stagnation pressure is composed of both the static pressure and the dynamic pressure combined together when you get a stagnation point there. So the velocity of the flow that came to stagnation at the tip of the pitot tube is obtained by taking the total pressure, that's what you measured on the pitot tube, minus the static pressure, and then taking the square root to get the velocity. That static pressure you need to know from somewhere. These are simple pitot tubes with no static taps, and as a result, you'll need to get the static pressure from the sidewall taps on this test section, and you'll need to interpolate to get the static pressure at the right location where you're making your measurement. There's two ways we can make measurements of pressure. One is we can use an electronic pressure transducer. This scanning valve here has 16 separate input ports that it switches onto a transducer to make pressure measurements from 16 different locations. As a raw unit like this, you'd need to do some interfacing, and we've already done that for you. We've put it into a box. We've connected with individual little tubes out to this front panel so that you can make connections here from the front panel to elements in the wind tunnel, like the 16 different pressure taps on the airfoil. And we've also got a power connection and a connection to the computer where you can do digital data acquisition to read the values that are coming in. Now, we'll get transient variable velocities in our wind tunnel flow with our flat plate because we're looking at a turbulent flow. And as a result, you'll get transient variable pressures measured on the scanning valve. That means that you're going to need to average those transient pressures so that you can get some average pressures and thus average velocity measurements from your performance. The other way we can measure pressure is using a simple water or oil manometer. If you take a simple vertical manometer, delta P equals rho G delta H, back from fluid statics in fluids 1. If you incline the manometer, you get more motion along the length of the manometer tube for a given change in the elevation, and the result is you can get more sensitive measurements. You can measure in centimeters or inches of water as a pressure indication, just the height of water on the manometer tube, or you can convert that to pascals, an actual pressure measurement with delta P equal to rho G delta H. You'll encounter three different types. There's this straight vertical manometer. There are these two inclined manometers, and there's a zoomed in version of them here. And then there's this inclined manometer bank, which can tilt back and forth and has many, many, many tubes here to allow you to compare many pressure readings at the same time. And it's scaled along the side here. There's not much complicated about these manometers, but you do have to check up on the practical physical details. Make sure you know what fluid you're looking at, what the specific gravity of the fluid is, whether you're working with water or with the lower specific gravity red oil. And what are the markings on the manometer scale? Are they inches or centimeters? Are they adjusted for the incline? Are they adjusted for the specific gravity of the oil? Make sure you know what you're measuring when you write down those details. Was the manometer inclined? What was the angle of inclination? Make sure there are no leaks in the tubes, either air getting out or water getting out. And finally, check to make sure there isn't any condensation in the tubes. If there's little bits of water caught in loops in the tube, that's going to change your pressure measurements. So as always, check the equipment before you test to make sure that things are working. And that goes whether you're working with a physical manometer like this, or if you're working with electrical and electronic equipment. Make sure you're getting good results before you go to make your tests. The first measurements you're going to do are for an airfoil. If we put an airfoil in a flow, we'll wind up with a pressure distribution over that airfoil. In this instance, much higher pressure along the bottom, much lower pressure along the top. So you're going to measure the surface pressure distribution, and that'll allow you to make some calculations about both the lift as a function of angle of attack and the drag as a function of angle of attack. You're going to measure the velocity deficit in the wake of the airfoil. So out front here, we have a uniform flow velocity. And in behind, we still have the same velocity in these regions out here that haven't been much affected by the airfoil. But in this wake region, we have a much lower velocity. And that's because there's been some drag due to the airfoil interrupting the flow. And if you measure how much velocity is missing, that's the velocity deficit. That tells you how much momentum has been lost, and that tells you what forces were acting horizontally on the airfoil. You're going to repeat this for various angles of attack so that you can cover the range on drag or on lift and drag coefficients. And you'll calculate some lift coefficients and drag coefficients from the measurements you make. The lift coefficient you'll be able to get directly from integrating the pressure over the surface. But for the drag coefficient, you're going to need to do a momentum balance for that velocity deficit, the missing momentum in the wake of the airfoil. And finally, you're going to make some comparisons to published results. Now, this particular picture of the airfoil here is showing it at a high angle of attack. It's not aligned with the flow. It's tipped up a lot with the flow. And as a result, the flow separates off the top here. And so it's a fully separated flow. This is a fully stalled wing. And when you have separation like this and you get stalled, you'll see a sudden drop in the lift produced by the wing. That can have really bad consequences if you're flying. So here, as we increase the angle of attack, we see that suddenly we see a decrease in the lift coefficient. That's because of stall, that's because of that separation, and that could lead to you falling out of the sky. Always a bad outcome. So to understand what's going on with those airfoils, we need to think about the forces that are acting on the airfoil, where the fluid interacts with the solid. And fluids can apply forces to solids in two ways. Pressure forces, normal to the surface, so always inwards, always at 90 degrees to the surface, just as we learned in the first fluids course. Now, in this diagram here, it's showing the pressure forces relative to atmospheric pressure. So positive on the front and along the bottom here, and negative, that is lower than atmospheric pressure, along the top here. So we're using atmospheric pressure as the datum. There's an angle of attack, in this case a very small angle of attack, the orientation of the flow relative to the chord line of the airfoil. The other way that we can exert a force is shear force, and that's parallel to the surface. That's due to viscous friction. And the higher the viscosity, the higher that viscous friction is going to be along the surface there. If we take a small surface element, say from about here, we can pick it out and say this surface element has shear stress in that direction and pressure force acting in this direction over this small little elemental area. And if we just go around the whole surface, considering each of these small elements at a time, we can find the small elemental force of drag on that one little area due to pressure on the projected area in the direction of the flow, and shear stress on the area in the direction of the flow. And we can get the lift as the pressure force on the area in the direction perpendicular to the flow. That's where we wind up with this sine theta angle. And the shear stress on the area in the direction perpendicular to the flow. That's where we get cos theta coming in. So lift is defined as being perpendicular to the flow, not to the airfoil, but perpendicular to the flow. So in our wind tunnel, always in this vertical direction, and drag is defined as being parallel to the flow, so always in this direction. So even if we change the angle of attack, the lift direction is still always up, and the drag direction is always still to the right in the direction of the flow. If we want to know the total lift and drag force, we need to integrate all of those little elemental forces to get the final results for drag and lift. If we can measure both the pressure and the shear forces, these ones and these ones, then we could just do this integration over the surface and be done with it. However, we've got a problem because shear is really hard to measure on a surface. So that's where we're going to need to do some fancy footwork. Once we've got the forces, we can then go and come up with dimensionless lift and drag coefficients so that we can compare different airfoils which are the same shape but may have different length scales, and be able to predict the performance of a big aircraft from tests of a small model in a wind tunnel. Now, this is exactly the same drag coefficient approach that you used in first fluids course, but it's important to note that when we look at wings or when we look at flat plates and boundary layers, we're always looking at the planform area. That is the span times the chord length for wings and plates, rather than the frontal area of bluff bodies like cars or submarines that we might be looking at drag coefficients for in other applications that we've seen. These are the equations for the lift coefficient and for the drag coefficient, and they look a little complicated with this added 2 down here. It is, as noted by XKCD, essentially just a decorative constant. It comes about as a result of carrying over from the factor of 2 that we have in our v squared over 2g in the Bernoulli equation. But this is the traditional definition, so you will see that factor of 2 in there. We can use our pressure measurements that we make at 16 distinct points on the airfoil to estimate those integrals. These equations here may look really complicated, but they are essentially just taking the integral equations that we had before and converting them into discrete summations over all the little individual elements of area associated with each pressure tap. And there's a lot more detail in how to approach this in the lab write-up, where these equations are taken from. Important notes here. This C sub P, this is a pressure coefficient. Once again, a non-dimensionalized pressure, and we're looking at the difference between the local pressure and the free stream ambient pressure, and comparing that to the dynamic head with this factor of 2 in there again. The devil is always in the details. We need to make account of the angle of attack in all of these elements. And we also need to allow for the fact that each of the individual elements on our airfoil is facing in a different direction. So all of these are oriented differently. And this angle phi here is the orientation of a particular element of the airfoil relative to the chord of the airfoil. Now that was getting us the pressure force effects on lift and drag, and lift is almost totally due to pressure, so we don't really need to worry about the shear stress effects on the lift. The wing is almost always oriented more or less in line with the flow, so the vast majority of the shear effects are oriented in the drag direction. So we can say that the lift coefficient is really very close to the lift coefficient that we get just by considering the pressure. Drag, on the other hand, has major contributions from both the pressure, the bluff body drag, and also from the friction drag from the skin, from the boundary layer. So we would need to calculate both of those. And we don't have a way of really doing this viscous drag element. So instead, we're going to have a look at a momentum balance over the entire control volume around the wing. At the front of the wing, we've got a uniform flow velocity, and as it passes over the wing, this wake region is missing some velocity. That means it's missing some momentum. So if we drew a control volume, just like we did in the first fluids course, we'd see that the momentum coming in was higher than the momentum going out through the backside of that control volume. That missing momentum is due to the drag forces, all of the drag forces combined, both pressure and viscous drag, on the airfoil, slowing down this fluid. So if we can just measure the difference between the free stream velocity here and this reduced velocity in the wake, then we can calculate the force of drag on the entire system. And the only place where this U minus U component is not zero is this region in the wake. So we can do that integral numerically from the discrete points of velocity that we've measured in that wake and get an estimate of the total drag force. It assumes that the pressure at 1 and the pressure at 2 are the same, and that there's no shear in the outer flow region out here where the boundary layer doesn't reach and the wake doesn't reach. Those are both good assumptions for an airfoil in an open flow in the open air. S is the span of the airfoil because the force depends on the pressure over an area, which is the length in this direction and the span in the spanwise direction. So that will allow us to get the total drag. We've already found out how we can estimate the pressure drag. From that, we could pull out what the other contribution was, the skin friction drag. Possible problem for those of you who remember from first fluids, we had to account for all the forces when we did a momentum balance. And we had pressure forces. So what if there was a difference in pressure between the front and the back? That pressure difference isn't there in an open flow with no boundaries. But our airfoil and our wind tunnel walls both have boundary layers where the fluid is slowing down. And that means that if the fluid slows down near the walls and on the airfoil, then if the cross-section is constant, the fluid flowing here in the open area has to speed up. Likewise, the airfoil thickness blocks a little bit of the cross-section of the wind tunnel. And as a result, the flow has to speed up. So the free stream flow, the U infinity, increases from here to here. And the pressure goes down to match. The pressure from there to there decreases according to Bernoulli's equation. Fortunately, it turns out that we can, if we just use the U infinity at the downstream location to calculate our momentum deficit instead of the U infinity at the upstream location, we can ignore the pressure and the two effects cancel each other out. And you're welcome to do the rather more complex integration that goes along with that. So that's what we're going to do for the airfoil. Once we've got the airfoil, we'd like to understand a little bit better about what's going on in the boundary layer that leads to that viscous drag. So we're going to make some measurements on a flat plate. And our objective with this flat plate are to measure some velocity profiles close to the plate. This is a classic fluid mechanical flow. One of the reasons it's a classic is because it's analytically tractable. You can actually do some pencil and paper calculations and get some pretty good results. Once we've measured the velocity profiles, we'd like to recognize in those profiles some of the basic boundary layer concepts, such as there's wall shear stress, which is causing the skin friction drag. And on the flat plate, that's 100% of the total drag. That's the only thing that's going on is skin friction. So it's not like the airfoil where we had a combination of pressure or form drag, bluff body drag, and skin friction drag. There's transition to turbulence in the boundary layer, and it's related to the roughness. And in this instance, we put some sandpaper at the leading edge to make sure that we get into a turbulent boundary layer. And that turbulent boundary layer is going to have velocities that are fluctuating, so we better make sure that we average our pressure measurements. Now, our manometer measurements will average things inherently because the water doesn't move that quickly in the tubes. We want to recognize that we can talk about the boundary layer thickness as just the distance out to where we get to 99% of the free stream velocity. And we'll also look at the displacement and momentum thicknesses that you'll be talking about in more detail in your second fluids course. Finally, we want to look at the links between our boundary layer on a flat plate where it's simple and manageable and easy to calculate, and the more complex flows and the separation that we see on airfoils where we have adverse pressure gradients. And that's something you'll go into in more detail, the reason for that separation in your fluids course. So here's a flat plate boundary layer. There's no pressure gradient, so the pressure doesn't change from here to here. The near wall flow is slowed down due to the shear stress, but the outer flow just continues on at the same velocity. It hasn't been affected at all due to the shear stress. We can still write Bernoulli's equation out here in this region. Now, if this flow in here is slowing down, then there's some missing mass flow, just like there's missing momentum flow. And in order to have mass be conserved, that's going to push the entire boundary layer, the entire outer flow further away from the wall. So the result is the streamlines will go upwards like this. The distance that they're pushed out is the displacement thickness, and that displacement thickness is just a dimensional representation of how much mass flow is missing down in here compared to what would be there if the velocity profile was still u infinity all the way to the wall. So it's an integral of this area in here. That's 1 minus uy over u infinity. That's the relative magnitude of that area that gives us a sense of how far out have we pushed the other streamlines. Momentum thickness is another idea. It goes in the same direction with us looking at not just how much mass are we missing and what's the associated dimension, but how much momentum are we missing. So in this case, we're going to be looking at the missing velocity component, and we're going to multiply it by the velocity. So there's the missing mass times the missing velocity. That gives us the missing momentum. And so the momentum thickness is a dimensional representation of how much momentum is missing in the boundary layer compared to what would be there if the flow hadn't been slowed down. And that missing momentum has been removed by the shear forces all along the length L, all the way from the leading edge and all across the breadth B of the plate, so that this momentum thickness integrated over the velocity profile gives us the drag force associated with the whole upstream area of the plate, because the boundary layer that we've got is the sum total of all of the effects that we've seen as we've moved from the leading edge of the plate down to the location where we're making our measurements. If we know that drag force, we can calculate a drag coefficient, and that drag coefficient is going to be dependent on the Reynolds number and the plate roughness. So in this lab, you're going to use the idea of momentum balance and missing momentum in both the airfoils and in the flat plate boundary layer to better understand how the flow is being affected by the shear stress as it moves along. This bibliography here will give you some background to follow up for review. And in addition, you should be able to find some other videos on the lab website that will point out some of the practicalities in getting the equipment to work in the lab. So best of luck with the lift and drag lab.